So our goal, we want to count total number of squares of all different sizes. And this is our data. So now we need to do data processing. To do data processing in our mind, so we need to do a lot of useful analysis work. Yeah. So at this point, we need to understand our data well. So this understanding step for our beginners. So now we treat ourselves as problem solvers. So we are beginner problem solvers. So for us, so we do not have a lot of experience. So we need to get a good training in this problem solving thinking. Yeah. All right. So for the understanding step, the first stage, so we need to, so what kind of work we need to work on? So several things we need to work. All right. First, understand our data. So currently, the raw data, so this is the raw data. The raw data is pretty messy, not organized. So if the data is not organized, when we want to work on it, it is very hard. So usually the first step, we want to find a way to organize our data, to arrange our data in a well-organized way. Then, the question, what's the benefit? What's the benefit to organize our data in a well-organized way? Yeah. So we will see it. What's the benefit? Yeah. So in your mind, now you just think about it. What's the benefit? Yeah. All right. So now, the critical step, how to manipulate the data efficiently. Yeah. So we need to do some operations on our data. Yeah. Manipulate the data. Yeah. Efficiently. So what do you mean? Yeah, because if we do not have a lot of experience, we have no idea how to manipulate efficiently. Yeah. So now we need to build up our experience. All right. Yeah, so arrange data in a well-organized way. Now the question, because even if you know you need to do this, even if you know you need to do this, the question is how to do it, right? How to organize your data in a, in a structured way. Yeah. So structure. Yeah. We want to build some structure on our data. If it is not organized, that means no structure built on our data. So we want to build a nice structure to arrange our data. That's the well-organized way. So how to build a structure? The next step. Important step. Okay. Characterize the data in suitable categories. Yeah. Because no structure, no category. The data of different types, the squares of different sizes, different locations, all mixed together. Or, in other words, all the data is placed in the same category, one category, right? One category. So, no structure there. Yeah. So, to build a nice structure, we want to define some nice categories. We want to choose appropriate categories to place our data. So that's the next step, important step. Yeah. So that the data in the same category shares the same property. Yeah. So why you need to put your data in different categories? Yeah. What's the benefit? Yeah. Now I can answer the question, what's the benefit to organize the data? Because after we put our data in different categories, then in individual categories, we can apply the same property. Yeah. Data in the same property, in the same category, it should share the same property, right? Same category. That's the point. If we put the data that belong to same category, yeah, if we define the category appropriately, then they should share the same property. But the data in different categories, they cannot share the same property, right? Yeah. That's the reason. It's hard to work on because no appropriate property can be applied on the global data, right? Yeah. Now, we want to apply some appropriate properties on a subset of the data. Global data, it's very hard to apply a general global property on it. All right. So now, next step, the definition of the categories. Now we need to consider what is the best categories we can choose for this question. Last time, one student already mentioned that. Here, I just recall it. Yeah. Taylor, right? Taylor, last time you talked about using sizes of the squares, right? Different sizes. Right. Yeah, 1 by 1, 2 by 2, and so on. Now, let's look at the sizes of squares. So we use the sizes of the squares to characterize our data. All the possible sizes we can find in this chessboard, 1 by 1, 2 by 2, 3 by 3, and so on. Total, we have 8 categories, 8 different categories. Now, let us distribute our data, our raw data, in these 8 different categories. How about that? How about that? Okay. Then, in each category, can you see all the squares in the same category, they should share some common property. Can you see that? The data in the same category, let's say 3 by 3 squares. Or let's consider all the 3 by 3 squares. Can we find a common property for 3 by 3 squares? Yeah, size 3, that's very rough. It's correct, but not in a deep sense. Yeah, so we want to dig into very deep understanding here. Yeah. 3 by 3, you only consider the size number. Do you consider the location number? No, location information? Yeah. Because location.
A 3 by 3 square can't have an upper left-hand corner square that is less than 3 squares from the right side of the chessboard.
Yeah. So that's your basic impression.
Right.
That's your basic impression. Now, we want to understand, much more accurately. Now, all right. 3 by 3. Yeah. So here, I just I just try to, let me draw a 3 by 3 square. 1, 3, this is 1 3 by 3 square. All right? Representative of all the 3 by 3 squares. What property can you find one simple property for this square? Yeah, area is, yeah, definitely, it's a property. Yeah, it is a property. We can find many properties. Yeah. But the question, if this area equals 9 units, okay, 9 unit squares, if this property is useful for our counting, our goal is counting, right? Yeah. So it may not be very useful. Yeah, it is one. So that's why we need to find the critical property, okay? The property that is helpful. Yeah, we can use the property. Okay, all right.
Coloring.
Oh, you consider, color, black, white, pattern, the pattern information. Yeah. Do not go too far, right? Even farther than the area, right? That kind of thing. All right, so here, let's look at this. 1 square, simple geometric figure. 4 sides are equal, right? 4 sides are equal. So let's understand this geometric figure, 4 sides. And there are 2 horizontal sides, right? 2 sides, horizontal sides. 2 vertical sides. Can you see some property related to horizontal sides, vertical sides, that kind of property? Yeah, right angle, it is one. But is angle information important for our counting? Yeah. So we just focus on the information that could be useful for our counting. So we stick to our goal, okay? So we do not, just pick some random properties. Got a lot of distractions.
Like the bottom left square could never be the right columns.
That kind of, So here we want to consider the general property, okay? Because the location of the square could be anywhere, right? Could appear anywhere. So we should not, stick to the location information. Location information is not important. We should not look at the location information. We look at the, some quantity information.
Think about like how many times 3 can fit in 8.
So, all right. So we have done some mental work already. Here, let me point. Oh, you want to say something?
The answer, like 6 times 6 for this, so 36 different squares.
Good. Yeah. Actually, he said 6 times 6. Do you know what's the meaning of that? He said 6 times 6. That's the total number of squares of 3 by 3 size. 6 times 6. He gave the answer. Counting on how many squares of size 3 by 3. He gave the answer. 6 by 6. Yeah. So if you cannot see it, good. Yeah. So very good. Good progress. Yeah. Yeah. Yes, I know you understand it. But for most students, you do not understand, right? How to get that, right? Too abstract. Yeah, too abstract. Yeah. So quickly we will get there. Yeah. That's a very, very, very good work. Yeah. Very good. Important progress. All right. Look at the difference between the distance of two vertical sides. What's the difference? 3 units. All right. What's the difference between also 3? Are they the same? They must be the same, right? All right. Yeah, square must be the same. So that's one property, right? So this property should be useful, right? Yeah? So it should be useful. All right. There is another important step. So here you can see our mental analysis work, how important it is in our problem solving. How important it is in our problem solving. We need to do a lot of work. Okay, all right. So now, another thing. In general problem solving, there is one step. We want to simplify the original problem. That's a general. Simplify original, because if the given problem is relatively hard, then in our human intelligence, we have the experience. We should find a way to simplify the problem, make the problem easier to work. Is that a natural way of thinking? Right? That's a natural way of thinking. All right, here, we will do that. Natural way of thinking, simplify the problem. How to simplify it? Yeah. Currently, we count the number of squares. Square is a two-dimensional figure, right? Two-dimensional figure. Can we separate it to one-dimensional, horizontal dimension, vertical dimension? We separate these two dimensions. How about that? Yeah, we separate. After we separate these two dimensions, the problem should be simpler, right? Yeah. One-dimensional problem is much easier than two-dimensional problem, right? Two-dimensional problem should be much easier than three-dimensional problem, right? Yeah. Yeah. So here, let's do another important mental work. So we split. We consider horizontal dimension, vertical dimension separately. How about that? Right. Horizontal dimension, the length of each side is 3, right? The length of each side, 3. All right. So that is a one line segment with length 3 units. All right. Now the question, if we count along the grid, horizontal direction of the grid lines, so just along this line, okay? How many line segments with length 3 can you can find? 6. Oh, good answer. 6. Can everyone see it? 6. 6. Oh, let me draw it. If some of you cannot see it quickly, let me draw. First one, second one, third one, fourth, fifth, sixth. Right? Yeah. 6. We allow overlapping. No problem. It's legal. When we do the counting, we allow overlapping. That's part of your understanding. We allow overlapped line segments when we do the counting. Yeah. Because for some students, because last time when I used 2 by 2 square as the example, then some students only count non-overlapped 2, only 4. But that means your understanding is not quite right. Your understanding is not quite right. why we cannot consider overlapped line segments, right? Yeah. Nobody stops us to include non-overlapped line segments. Then we can do it. So here, understanding is very important. So based on our understanding, 6 different line segments with length 3 horizontally. How about a vertical counting? How about vertical counting? Yeah, also 6. Symmetry. This time, yeah, because this figure, it has very nice symmetry property. So we should take advantage of it. Yeah, very good. Yeah. Then can we combine? Horizontally, our counting number is 6. Vertically, counting number is 6. Now we need to go back to 2-dimensional, counting 2-dimensional figures. 6 times 6. That's his answer. Okay? Yeah. Yeah. So in one category, we get an answer, or we get a part of the answer for one category, right? Can we do the same thing for all 8 categories? We can do the same thing on all 8 categories. Then we know we can find a final answer, right? In this way. Yeah. So let's complete it. Let us complete this whole question. All right. Now, main work. We need to do counting. Right. So here, square in various sizes. Now I want to do a chart. Yeah. Based on our analysis. Now, do you agree at this point we have much better understanding? Yeah. After this kind of discussion, we have much better understanding. Now, let's do some summary. Yeah. All right. Size column, we have 8 different categories. Size column. Then the second column, number of squares for these 8 corresponding categories. Right. How many 1x1 squares? 64. Good. 64. But here I use the, I separate horizontal, vertical dimensions. Yeah. Yeah. The reason is very simple. The reason, because later we try to derive some more important property. In this way, because there is a possibility we can find some very important property. Yeah. You will see it soon. Then 2x2, 7x7, right? Yeah. So and so on. Okay. So I think after you observe the rule, yeah, it's very easy. You can get a counting numbers for all 8 categories. Yeah. So, but the next question. Now, when you look at the data on these 2 columns, compare a little bit. Can you see some interesting property between these 2 columns of data? Reverse, good. Yeah, reverse, yeah, that's a nice property. Yeah, that's a nice property. So is there any other interesting property you can see? So here, because the reason I want to introduce a very important concept here based on this observation. All right. Observe a rule. The rule here is we have size number and number of square. We have a number, right? The size number, 3x3, 4x4, I only take the size, one size number. Okay? So the number of squares, in a 2-dimensional case, I only take the 1-dimension number. Okay? Yeah? Because I want to find some relationship between these two numbers. Relationship between these two numbers. All right. So size, let us use a general representation, n by n. General representation, size. Yeah. Representing all different 8 sizes. Number of squares, let us use n times n. General expression. Can you see any relationship between m and n? These two numbers.
It's always 9.
Yeah, the sum of these two numbers always 9. Yeah, if you can see it, this is some intrinsic property. Yeah. So m plus n equals 9. When you change your size number, counting number, yeah, it is always 9. When you're going through all 8 different categories, the sum number never changes. What's that? It never changes. So I'm sorry?
It's invariant.
Great. Invariant. This concept is extremely important. This number does not depend. Well, so here we need to learn a concept called invariant concept. Yeah. Yeah. Invariant concept. So some quantity never changes when you change your data in different categories. That quantity never changes. This is the concept. So this concept in problem solving, very important. Yeah. So here I want to explain the importance of this concept, invariant concept. Yeah. All right. Invariant usually provides critical property or insight of this problem. Yeah. But how do we use it? Yeah. One way to use it, we can use this invariant property to keep track of the data. Keep track of the data. Yeah. Because when we, navigate through different categories of the data, we may get lost. We may get lost. How to keep track of our data? Yeah. This invariant property can help us. So this is one of the usages of this concept. Yeah. Let me give you one example here. So you can see how to keep track of the data by this invariant concept. Consider 100 by 100 chessboard. So let us generalize our chessboard. Yeah. Very big one. 100 by 100. You can only imagine it. Okay? All right. Now the question, think about, we want to count the number of squares of different sizes in this big chessboard. All right. When you do the counting, so here, I do not ask you the total number of squares. I only ask you for one category. How many squares are of the size 37 by 37? So 64, not 3. Yeah, only one short. Only one short. Yeah, yeah. But how do you know 64 square? That many. How can you see it? Think about, how can you see it? Here, you need to look at the invariance number for this case. The invariance number, the size number plus 1, right? 101. Yeah. In our previous question, 9. How to get a 9? 8 plus 1, right? 8 plus 1. That's the 9. Here, we change the size of the chessboard. The size becomes 100. So the invariant, that number should be 100 plus 1, right? Yeah. That means this 37 number plus that n number should equal to 101. 101. So 101 minus 37, 64. Yeah. That's the way. Yeah. How do we keep track of the data? How do we keep track of the data? We use this invariant quantity. Yeah. Otherwise, imagine if you do not use this invariant concept. How do you get this 64 squared? It's pretty hard, right? It's pretty hard. Because in your mind, it's very hard to draw that big chessboard, right? Yeah, you can draw on your scratch paper. You can still find the answer, but much slower, right? You need much more time. Yeah. But by this invariant, this concept, yeah, some students can get an answer quickly. Think about that. How important is this concept? Okay? Yeah. All right. Yeah. Yeah. All right. So then, now we want to complete the final calculation. Yeah. The final calculation, the total number of squares, so we add up the squares of these 8 consecutive integers. Yeah. So then, so you can, calculate carefully, you get a 204. Yeah, but here, if we consider the general question, yeah, so this question we consider general n by n size chessboard. We want to count total number of squares in general n by n chessboard. So based on our analysis, work, so we need to do this summation, right? Yeah, we need to do that summation. Summation of the first n consecutive square of consecutive integers. Yeah. There is a formula. There is a summation formula. Yeah. 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 So, how to get that? So, we do not need to derive it. Yeah, so here we use this formula. Yeah. And there is another formula we use quite a lot in this class. Yeah. That's the summation of first n consecutive integer, not square, first n consecutive integer. Any of you know what's the answer, the formula? Summation?
Like in sigma notation?
Sigma, but I want this final answer. In terms, the formula in terms of n, not the sigma notation. Any of you know this? 1/2 times n plus 1? Yeah. Because in your discrete math, you learned these formulas. Yeah. Yeah. So especially this one, because this one we use quite a lot. So here I need to review it. All right. Yeah. So your discrete math. So there is one section talk about summation of n consecutive numbers, n to the k, not just 2, n to the k, general n to the k. Yeah. All right. And here, I may also give you another interesting formula. 1 cube plus 2 cube first n consecutive cubes, this formula. Yeah. Because it's not easy to memorize formulas like these, yeah. Especially after a long time. Yeah. So how can you memorize these formulas after a few years, right? Yeah, it's hard. Yeah. So you need to, based on some interesting properties, usually to memorize the formula, you need to base on some very interesting properties. So here, what's the property, interesting property we can use to memorize this formula? First, you need to memorize this formula because it's very basic. Yeah. So everyone should memorize this formula. Okay? Yeah. To begin with, yeah. You have to. Okay? So this formula for our computer science students. Yeah. So we have to memorize it. All right? Yeah. Then this formula, what's that? Square of, so that formula, look at this. This whole thing square. Just this one, we square it. That's interesting, right? Yeah, the square of it. Yeah. If you connect to this property, then you can always memorize that formula, right? Yeah. Yeah. So that's the, yeah. Why? Some people can memorize a lot of things because they're based on some interesting properties. Yeah. Yeah. Otherwise, if you do not connect, something to some special properties, very hard to memorize. Yeah. All right, yeah, so we complete this topic. All right. Next, 8.2. Yeah. Another topic, prime factorization. Our second computing problem in this class, given a positive integer m, how to represent it as a product of prime numbers. Yeah, so that's the prime factorization. Yeah, all right. Yeah, so so this topic I select from section 11.3. Yeah, it's a very late section. Yeah, yeah, but because we can understand it easily. Yeah, so I select this topic. And later, remember in the first class, I mentioned I will give you an optional project. So this topic is the first half of that optional project. All right, let's do some analysis. How to do the factorization. First, we need to understand the problem. We need to understand the prime numbers. First, definition of prime numbers. All right. Prime number is a natural number. First, natural number greater than 1. Not a 1. 1 is not a prime number. Now we call it a unit number. 1 is the unit. So it's not a prime number. That has only 2 factors. Only 2 factors. 1 and itself. 1 is always a factor of any integer. So itself is also always a factor of itself. Yeah. So other than these 2, no other factors for prime numbers. Yeah. Example, yeah, so these first few examples of prime numbers. Yeah. All right. A composite number is a natural number greater than 1 that is not prime. Yeah. So the definition of these two types of numbers. Yeah. All right. So we want to study these two types of numbers. It has more than two factors. Yeah. Other than 1 itself, there is some other factors. Yeah. So that we have some simple examples. Yeah. All right. Now the question, yeah. Because when we understand this topic, so we need to ask a few questions. The first question: is it true that for a given natural number, yeah, so what's natural number? Yeah, because actually for the meaning of natural number could be slightly different in different places. Yeah. Some places it includes 0, but some places not including 0. Now here, obviously not including the 0. Yeah. All right. So positive integers, if it is not a prime, then it must be a composite number. Is it true or not? This statement, true or false? That's why. So that's what I said. In our understanding step, we need to pay attention to the little things. Yeah, I heard many of you said true. Think twice. Is it true? Think twice. Pay attention to the little things. How about 1? How about 1? 1 does not belong to prime numbers, right? 1 does not belong to composite numbers, right? So 1 is unit. Yeah, I mentioned 1 is unit. So we take out the unit number. Then all the remaining positive integers then either belong to prime numbers or composite numbers. But 1 is a very special number. Yeah. All right. Another question. For a given natural number, how to determine if it is a prime? Yeah. Yeah. So it's a basic operation. Given a very large integer, you can imagine. Some integer with hundreds of digits, a huge number. You can use your computer to do the work. Still a lot of work, right? How to determine if that given number is a prime or not?
Prime sieve.
Oh yeah, good. Yeah, so, yeah, we will get there. Yeah, we will get there. We will get there. Yeah.
Dividing every number.
Yes.
To the square root of that one.
Yes. Oh yeah, square root. Yeah. So you too know a lot. Yeah. Good background. Yeah. Very good. We do factorization. All right. How to do factorization? Basic operation. Here. Yeah. Basic operation. Because I use this example to explain some important points of problem solving. Yeah. So I want to convey some general ideas in problem solving. Yeah. All right. Basic operation related to factorization. We factorize n given positive integer n as a product of AB factors. Two factors, AB factors. Okay, yeah. So and we try to get factorization A and B, two positive integers between 1 and n, but strictly greater than 1, and strictly less than n. Between AB, we want to make A less than or equal to B. So after we put this kind of reasonable conditions there, yeah. So then, because that's the factorization we are looking for, we want to We are interested in this kind of factorization. Yeah. If we can get it, yeah, if possible, if it is possible, we can do that. So, yeah. Then, based on the definition, this n is not a prime, right? Yeah, if it's possible, if we can do this factorization, then we can say n is not a prime. Otherwise, n is a prime. And that's under the condition we can never find such A and B. If we try to get factorization of A and B satisfying this condition, but we fail, you know, after all the possible experiments, we fail. Then our conclusion is n is a prime. N is a prime. Yeah. So that's the, you know, basic understanding. Yeah. Yeah. After we understand this step, so our next step, we want to do the work. Yeah, we want to do the work. Yeah. Because in this optional project, you need to write the code. You need to write the code. For those who are interested in the optional project, programming project I mentioned last time, yeah, so you need to write the code. Okay, all right. The main step here, determine A and B with A in this range, in this condition, yeah, you know, constraint. Yeah. All right. Question, how to resolve the uncertainty? Yeah, because a lot of things uncertain. Too much uncertainty here. Yeah. So that's something I want to talk about in problem solving. Yeah, so in general, when we solve a problem, for the given data, there is a lot of uncertainty there. We need to deal with a lot of uncertainty. Yeah. Question.
Are you familiar with Dave's Garage on YouTube?
Mm-hmm.
It's Dave Plummer. He's a retired software engineer. And, he worked at Microsoft. He actually wrote the what do you call it? You control delete the task manager. He wrote the task manager.
Mm-hmm.
He's got a whole series of videos on prime sieves, and he does competitions with people like basically drag race two different prime sieve implementations.
Yes.
It's pretty
Yes. Yes.
If anyone's interested in
Yeah.
this, that'd be a
Yeah.
good resource.
So actually that, you know, the algorithm in that direction are very complicated. Very, very complicated. So for this class, we will not go that far, yeah, because extremely difficult. Yeah. People use a lot of knowledge in number theory. Yeah. The advanced algorithm rely on advanced knowledge in number theory, very deep knowledge. Yeah. So we will not, you know, go that far. Yeah. All right. Yeah. So now we get to this problem solving part. Yeah. How to handle the uncertainty. Yeah. So that's the general question in our problem solving. Yeah. Because for us problem solvers, yeah, so we don't like uncertainty, right? People like certainty. Yeah. Not uncertainty. Yeah. So the goal, we want to make it certain. Yep. So make our, you know, goal, destination. We want to make it certain. Yeah. So the idea, we want to find a way to reduce uncertainty. Yeah. Yeah. So we want to reduce, so make it more and more certain. Okay? More and more certain. Yeah. Yeah. How to do it? By exploring the properties. So we need to discover some useful properties to reduce the uncertainty. Yeah, question.
What do you mean in this context for uncertainty? Because I'm coming from like a physics background, so I'm thinking like
Yeah, right. Yeah, physical. Yeah, so that you have specific meaning. But here we talk about the general meaning.
Okay.
Uncertainty. Yeah,
Like
in physics. Yeah, so you have some very specific meaning of uncertainty. Yeah, so there is some law, right? Yeah, yeah. Measure.
It's not
Not that. Yeah. Yes, we talk about the general meaning. Yeah, not a special meaning. Yeah, uncertainty. Yeah, physics. Yeah.
I think he just means like identifying all the characteristics to reduce your own uncertainty about the problem, right?
Right. So for our general audience, yeah. So not physics people. Yeah. All right. Yeah. So here, we need to discover some useful properties to help us reduce the uncertainty. Reduce. Yeah. So, all right. So what properties can we find for A and B? How can we, so here, we can treat this as the range for A and B. Yeah. So this range, relatively big. When the range is big, then a lot of uncertainty there. The question, can we reduce the range? Yeah. Question? Yeah.
No, just other answer to that. So the factors would have to be less than or equal to n divided by 2, right?
Mm-hmm. Yeah. Oh yes, that's one way to, that's one way to reduce the range. Yeah. N divided by 2. Yeah. N divided by 2, but you mentioned square root, right? So then even more reduction, right? Larger reduction. Yeah. He mentioned the square root of n. That's smaller than n by 2, right? N over 2. Yeah. So we will get there. So here, the point. So you know the point. We want to reduce the range for our data to be considered. Yeah. The smaller the range, the easier, right? Yeah, because you need to do experiments in a much smaller range, better than you do experiment in a large range, right? Yeah. So that's the difference. Yeah. The difference is in computation efficiency. In a large range, your computation efficiency is not as good as you work in a much smaller range of data. Yeah, so that point. All right. So, but if you cannot find any property, because here, so you two already mentioned 2 different properties. You mentioned 2 different properties. So these 2 properties can help us reduce the range of the data greatly. But if someone cannot discover any property, if some people cannot discover any property, then what you can do, you need to work on the original data range, right? You need to work on this whole range. Yeah. So no answer. That means you have no uncertainty reduction. Okay? Yeah. So then you need to try all the possibilities. You cannot miss anyone. Any possibility, you need to do one experiment. Okay? Test it and see if it works or not. Okay? So you need to do a large number of experiments, testing. That's the difference. All right? Yeah. 8.3. Sieve of, how to pronounce it? Good. Yeah, because for the class I practiced quite some time. Eratosthenes, right? Eratosthenes. Yeah, I practiced quite some time. It's very hard. Yeah. So let's look at this very ancient Greek algorithm. Very simple. Yeah. more than 2,000 years old algorithm. Yeah. All right. So here, so we look at this question from problem-solving point of view. All right. The basic operation n equals a times b. Yeah. So now we want to do range reduction. Yeah. All right. All right. So the original range like that. Yeah. So in the original range, we need to do a lot of work. If you do not do any reduction, you need to test all the possibilities. You need to exhaust all the possible cases. So that's a lot of work. Yeah. All right. So let's look at how much work we need to do without any reduction. All right. Yeah. So here we need to exhaust all the possibilities. Can we list all the possible data items we want to apply testing operations? No. So we need to do that. All right. Range of the data. Yeah. So here, yeah. So we consider A and B choose from in this range. Yeah. A and B in this range. Okay. But we have two factors we choose. Two factors. Like a two-dimensional problem. Yeah? It's not one factor, one dimension, one dimension. Two factors, two-dimensional problem. Yeah? So more work when one-dimensional problem, right? Two-dimensional, you need to do more work than one-dimensional problem. Now, let's list all the possible A-B pairs in this range, but our second factor B should be greater or equal to A. So we can, reduce slightly, but we need to list all those pairs. First pair, when we start, A is the smallest number in the range. B also the smallest number greater or equal to A. So that's the first pair. Second, we fix A. We increase the number in B, so we get the next pair, and so on. We fix A, the last B, we can put there n minus 1. Then we finish all the pairs with A equal to 2. That's all the possible pairs with the fixed A number 2. Next round, this is our first round. Next round, we fix A equal to 3. Yeah. Then we go through all the possible numbers for B, satisfying the constraint, and so on. Yeah. So we do this. Yeah. At the end, we list all possible pairs, right? Yeah. We list all possible pairs. That's the number of experiments we need to work. Yeah. So for each pair, we need to check if n equals A times B. True or false? We need that checking operation. Now, can you tell me how many tests do we need to do? How many pairs do we have here? How many experiments do we need to do? Can you see? Yeah. Summation, total number of pairs. We need to, when A is fixed to 2, that number we know, right? A minus 2, right? Is it A minus 2? A minus 1? Yeah, but not the first one. A minus 2. So we need to take summation, 1 plus 2. The last term is A minus 2. Because this round, A minus 2. This this one, when n equals n minus 1, only one pair. So one pair, this is one pair. Yeah. Then n equals n minus 2, two pairs, and so on. Yeah. N equals 2, n minus 2 pairs. Can you tell me what is the formula for the summation of these numbers? Yeah. Remember, we reviewed that formula before. We reviewed that. 1/2 times the total number n minus 2, right? Yeah. n minus 1, n minus 2. Yeah. That's the total number of pairs. This many pairs, we need to do the checking operation. Yeah. That's quite a lot. Yeah. Quite a lot. So the efficiency is not good. If we cannot find a way to reduce the range for our data, we need to do large amount of work. So our computation is not efficient. Yeah. This kind of computation, not efficient. Yeah. So we need to find a more efficient way to do the testing. Yeah. All right. All right, so let's continue. Yeah. Yeah. So here, let's study. We try to reduce the range. All right. So here, in this range, yeah, the numbers, either primes or composite numbers. Yeah, other than primes, remaining composite numbers. Yeah. Or the other way around, if we can select all the composite numbers, or if we can remove all the composite numbers, the remaining numbers, they are all primes. Yeah. So based on that simple fact, next we want to do is we want to remove all the composite numbers in the list. Yeah. All the composite numbers. All right. The question: how to select all the primes in above? Yeah. Because our goal, we want to select all the primes in the range. Yeah. Yeah. Yeah, because people are more interested in the primes. No question.
Start multiplying numbers together and removing from the list.
Yes, good. Yeah. So that's the ancient Greek people. Yeah. So they, based on the natural thinking, understanding, yeah. So they can do the work. When we do the prime factorization on n, yeah, use the primes in above. Yeah. So here, yeah. Because when we remove composite numbers, we get more and more primes stand out. Yeah? Yeah. At the beginning, primes, composite numbers, they are mixed. Yeah. So we do several rounds of composite number removal. Several rounds of composite number removal. Yeah. So, and more and more primes are exposed. Yeah. So, all right. Observation here. Yeah. The form of a composite number. Yeah. So here, we work directly on composite numbers. Yeah. So here, yeah. Another problem-solving commonly used method I want to explain. Another commonly used method I want to explain. Yeah. Today I cannot finish, but next time I will finish the remaining part. I just say a few words. Yeah. All right. In problem solving, when we have a situation, yeah. So here, yeah. I try to finish in 1 minute. I try to finish as a conclusion of today's class. Yeah. In problem solving, so there is one typical situation like we have here. So what's that? When we work on a problem, there are more than one cases to work. Here we have two cases to work. One is prime case. Prime case. We work on the data, we work on prime numbers directly. So that's one. Another case, composite number. We work on composite number directly. Two cases. Prime case, composite number case. Two cases. Which one is easier? Which one is harder? Yeah. So when we work on composite number, harder, easier, or prime number, harder, easier, yeah, there is a difference. Yeah. When we have these two options, then the rule of thumb is we always work on the easier case first. Here, composite number is the easier case. Easier case. So that's why we should work on composite number first. Yeah. Why composite number easier than prime case? Yeah, next time I will explain. Next time, first I explain why composite number case easier than prime case. Yeah. Then we have this problem solving practice, best practice. We always work on the easiest case first. All right? Yeah. So see you next time. Yeah. Monday, we complete this first.